In this lesson on mechanics for year one, we're going to have a look at displacement time graphs. And this is the start of chapter 9 on constant acceleration, or we're also looking at what you might call kinematics, so the study of basically things moving. Now, there is chapter 8 before this, which mostly talks about how we model situations in mechanics, and that is worth a read, first of all, before we start this chapter. I'm not going to do a lesson on it in particular, but it is worth reading through and just making some notes from some of the examples, perhaps. But I've put together some key questions from chapter 8 here that I just want to talk through, because these are all important. Now, I'll write down some of the answers, but not necessarily all of them. So what are the standard units for each of these? Now, standard units is important that we use these so we don't get confused between, well, this first one's talking about mass. We should use kilograms rather than pounds. And if we try and mix these two units, it's not gonna go well. So we have standard units that we use. So for mass, it's kilograms. For time, we tend to use seconds. For displacement, we use meters, or some sort of denomination of meters, so perhaps kilometers and so on, but we tend to default to just meters. Velocity is meters per second, so you can write that as ms to the -1, or you could write it as m divided by s, but I prefer ms to the -1. Acceleration is meters per second squared, or you could write meters per second squared like this. Okay. What's the difference between a scalar and a vector? So a vector has got magnitude, so size, and direction. So this is the difference between velocity and speed. So speed is just how fast you're moving. Velocity is how fast are you moving and in what direction. So you could have a positive or negative velocity. So if I was moving away from you, you might consider that to be 20 meters per second. If I was moving towards you, you might consider that to be minus 20 meters per second. So a vector has got direction, a scalar does not. We'll talk more about that in the next couple of lessons. If I take 3 steps forward and then 3 steps backwards, what is my displacement now? And what is the distance traveled? Well, these two words mean similar things, but one is a vector and one is a scalar. Displacement is the vector quantity. So if I take 3 steps forwards, so that's +3, and then 3 steps backwards, that's -3, my displacement is now 0 meters. What is the distance traveled? Well, that would be 6 steps. Okay, in fact, for 0 meters, I should write 0 steps, shouldn't I? But you get the idea. Okay, so if we stretch this example to your car measures the distance traveled. It doesn't measure the displacement. So when I travel 5 miles to work and then 5 miles home, it says that I've traveled 10 miles. If it was measuring my displacement, then by the time I got home, it would actually say that it was 0 again. So I would have gone +5 and then -5. And I've gone back in the same direction, which wouldn't be quite so useful. A particle is traveling at 3I plus 7j meters per second. What is the speed of the particle and what angle is it traveling at? Now, whether you've done vectors or not yet in the course, depending on where you are, let's just remind ourselves what this means. 3I plus 7j, we could write that as a column vector. You might have seen vectors written like that, where it basically means 3 right and 7 up. Okay? So overall, our direction is something like that. Now, to work out this green length, this is going to be the overall speed. It's going 3 meters per second that way and 7 meters per second this way. So its overall speed we can just find by using Pythagoras, because this is a right angled triangle. So that's 3 squared plus 7 squared, square rooted. So that's root 58, or 7.62. Okay, so we've got a speed of 7.62, but the velocity, which would be a vector, is 3I plus 7j meters per second. So speed is a scalar, velocity is a vector. Now for the angle, well, let's mark on an angle. Let's just put it in there for now. To find that angle, we could do inverse sine of opposite over hypotenuse. Or actually, let's do it with the two values we're given, because then that'll be a bit more accurate. Let's do it with the 7 and 3. So that means it would be inverse tan of opposite over adjacent. Okay, so inverse tan of 7 over 3, 66.8 degrees. Okay, we should also specify where that's measured from. So that's measured from the horizontal, or from the vector I. Okay, because I is the horizontal vector, which is 1 unit long, and j is the vertical vector, which is 1 vector long. Sorry, 1 unit long, which is why this works to be this diagram here. Okay. Now, a few modeling assumptions. These are important too, because in mechanics, we can never model anything 100% accurately. We have to make some assumptions to make our calculations a bit easier. So when we model something as a particle, what does that mean? So a particle means the dimensions of my object are negligible. So we're just considering it to be a single point. So if I modeled a football as a particle, I wouldn't really be worrying about how big the football is. I wouldn't take that into account. It also means its mass acts at a single point. And it means that things like rotation and air resistance can be ignored. Air resistance is probably the biggest factor there, though. If we model something as smooth, what are we assuming? Well, we're assuming that there's no friction when we say smooth. Okay, it can just slide over each other without any friction. If we model something as an inextensible string, what are we assuming? So we're assuming that our string does not stretch. It doesn't extend at all. And that's important because if I've got two particles that are attached with this magical piece of inextensible string, it means that they will accelerate at the same rate. Perhaps in your head, imagine if I had two particles attached by a stretchy string, maybe like an elastic band. When you pulled one, there would be a delay before the other moved, and they would accelerate at slightly different rates. So if we've got a string which doesn't stretch, i.e. an inextensible string, then that means that they do accelerate at the same rate. The last one, question 8. What is the value of acceleration due to gravity? That's something that we call g. We tend to use for the constant, the acceleration due to gravity. And we use 9.8 meters per second squared. Okay. And if we are not looking at air resistance, then objects will always fall at 9.8 meters per second squared, no matter how heavy they are, as long as we're not taking into account air resistance. Okay, and we'll talk more about that in a lesson or two's time. Now, what I want to focus on in this lesson is just these values here, S, V, A, and T. What are these letters then? So S we use for displacement. Now remember, displacement is the vector form of distance. So displacement can be positive or negative. Remember that last example, if I walked 3 steps forwards and 3 steps back, my displacement would be 0, but my distance might be 6 meters covered. Okay. V we use for velocity. Again, that is the vector form of speed. So it's speed but in a given direction, so you can have a positive or a negative, or you could even write it as a vector with I and j components. A we use for acceleration. And again, that is a vector. We don't really have like a different word for the vector and scalar forms of acceleration. They're both just acceleration, but in mechanics, we tend to use it as a vector. So it could be positive or negative. So something speeding up or slowing down. And then T is obviously time. Now time, not really a vector. Can't really deal with negative time. Haven't really invented any time machines yet. So time we can just use as a scalar value. Here I've got 3 displacement time graphs. So I've got S on the y-axis measured in meters, and then I've got time on the x-axis measured in seconds. Now let's just think about what's going on in each of these contexts. So in the first one, this one here, the displacement is not changing. If it's a flat line, the displacement is staying the same. So this object is at rest. Okay. In the next example, the displacement is changing with time in a linear fashion. Okay. So it is moving at a certain speed. It is moving at a certain amount of meters per second. To work out its speed, you could find the gradient, because I could find the change in y over the change in x. Now the change in y is going to be measured in meters, because that's on the y-axis. The change in the x-axis is measured in seconds. So my units for the gradient are going to be meters per second. So we can tell that the gradient of an ST graph, or a displacement time graph, is going to be the velocity. That's a really important fact. The gradient of a displacement time graph gives you velocity. Now this next one is a curve, so it is increasing. But let's think about the gradient at some different points. If I drew on a tangent here, so if I drew a tangent there, okay, it looks a bit like that. If I drew a tangent here, maybe let's do a different colour. Let's go for green. It's a bit steeper, isn't it? And if I drew a tangent up here, then it's very, very steep. So the gradient, i.e. the velocity, is increasing. So let's just make a note of that. So the velocity is increasing. Therefore, that must mean it is accelerating. Okay. So here, it has no velocity because its gradient is 0. Maybe we could make a note of that. The gradient is 0 here. It's a flat line. Here, the gradient is constant. The gradient's always the same. So therefore, the velocity is always the same. And here, the gradient is getting steeper and steeper and steeper, so it's accelerating. Okay. So that's the first important fact, is the gradient of a displacement time graph gives you velocity. Here's an example of a displacement time graph with a bit more context to it. So it says a cyclist rides in a straight line for 20 minutes. She waits half an hour, then returns in a straight line to her starting point in 15 minutes. This is a displacement time graph for her journey. Work out the average velocity in each stage of the journey in kilometers per hour. So remember, this is displacement up the side and time along the bottom. So the first stage, so up to here, let's find the average speed. So we've got, it's gone from 0 up to 5. So that's 5 kilometers in 20 minutes. Now we don't want to do it in minutes because we want the speed in kilometers per hour. 20 minutes, that's 1/3 of an hour. Okay, so we can divide it by 1/3. So that's going to be 15 kilometers per hour in section A. Okay, let's look at the next section. Well, from A to B, the displacement stays the same, so the velocity is 0. And for the last bit, B to C, let's find the gradient. So we've got a change of 5 kilometers again. And then the time goes between 50 and, we've got the time, so it says this was 20, then it waited for half an hour, so that's up to 50, and then this bit's 15 minutes. This is going to be 65 here. So that's 15 minutes, which is obviously a quarter of an hour. So I'm just going to write a quarter, or you could write 0.25. So that's going to be 20 kilometers per hour. And it does ask for a velocity. So the velocity has to have direction, and if they're coming back towards the start point, then we could call this minus 20 kilometers per hour. And that makes sense in terms of the gradient too, because the first section had a positive gradient, it went upwards from left to right, whereas B to C has a negative gradient, it goes downwards from left to right. Okay, part B write down the average velocity for the whole journey. The average velocity for the whole journey then. To do that, we can just look at the total displacement over the total time. So let's make a note of that. The average velocity is going to be total displacement over total time. Now the total displacement, well, we started at the beginning, we went out, and then we came back to the same point. So the total displacement is actually 0 over 65 minutes. Doesn't really matter what's on the bottom. I'm going to put 65 minutes, but the answer is going to be 0 for the average velocity, which seems slightly counterintuitive, doesn't it? But it's because we're talking about velocity rather than speed. Now part C, the average speed. There, rather than using total displacement, we can use total distance. Okay, because remember, distance is the scalar form of displacement, just like speed is the scalar form of velocity. So the total distance that we've covered, we did 5 kilometers in the first bit, then we did 0, and then we did 5 on the way back. The total time was 65 minutes. What's 65 minutes? That would be 6 and a 12th, basically, wouldn't it? I'm going to write that as 6 and 1/12, because 5 minutes is 1/12 of an hour. Then we can work out this fraction. So 10 divided by 6 plus 1/12. We get 1.64 kilometers per hour would be the average speed. So depending on your context and what you're actually trying to find out, some of these might be useful, some of them might not be. If I was testing the performance of a car and I'm going to do a loop where I go out to work and come back, then velocity is not going to be particularly useful because it's going to tell me the average velocity of my car is 0 kilometers an hour. I'm probably going to be more interested in my average speed. But it just depends on what context you're looking at. Okay. Have a look at exercise 9a, just for some practice reading, interpreting, and making calculations based off of displacement time graphs. Okay.